So this one's called Connectionism and Cognitive Architecture, a Critical Analysis. And both these papers were written in 1988. This one's by Fodor and Pylyshyn at the Rutgers Center for Cognitive Science. So this is the symbolic argument. So first, what is a connectionist system? So the connectionist systems are networks with large numbers of simple but highly interconnected units. And there's certain assumptions made about the units and their connections. Usually the unit receives real valued activity, like a continuous activity along its inputs. And the units almost always sum this activity, sum their inputs, and then change their state as a function of the inputs. And so each connection is allowed to modulate the activity coming from a node, and that's called the weight on the connection. So I think everyone here is familiar with. I mean, when they talk about connectionist systems, we're basically just talking about what we call neural networks in computer science. And though this idea has been explored since the very beginning of AI, like in the 1940s when computers and AI were being talked about together, it was not until somewhat later in the research when they invented backpropagation and better hardware that the connectionist ideas started producing the valuable results. And this was in the 1980s. And so when this happened, the approach gained major popularity. So when this paper was being written, the connectionist approach had gone from a fringe viewpoint that almost no one was really working on to a nearly universal popularity at the AI conferences. They said the AI conferences look like connectionist pep rallies. So the explosive success of these connectionist networks was due to its appeal to several scientific groups. So for the philosophers of computational psychology, there were skeptics of folk psychology. This is kind of what symbolic AI is based on, which is these are the people who believe that ideas like explicitly representing goals and beliefs and intentionality, that these are too abstract, that you can't actually explicitly specify these in a system. And so they like connectionism because it provides a more like rigorous mathematical or scientific approach to modeling cognition. And then on the other hand, the people who actually thought the symbolic AI systems were too computational, too rigid, they're too much like computers, they don't act enough like the human brains. They like connectionism for like the other reason, basically, because it addresses basically more direct computation with sensory data. More like grounded, like realistic like application versus something that's more abstract and computational. And so that was one group, computational psychologists. So another group was obviously AI scientists, because there had been at this point a lot of failures with the traditional symbolic systems, even actually like after major business money had flown into like the research field from like industry. And so this resulted in what we know as the AI winter. And so during this time, people became skeptical of AI scientists. And so funding was really hard to come by. And so the connectionist methods provided hope to AI scientists who think that the serial machines are too weak, basically that the symbolic idea is kind of outdated. We've tried it. And now we have to replace them with radically new parallel machines, which is a lot of the appeal of the neural network, is that everything works in parallel, which is also why it required the new parallel hardware to be invented. And then obviously biologists and neuroscientists would like this idea because they work with, like when they think about cognition, they're only thinking about biological neurons, so neural networks by definition. And then, of course, young scientists tend to have anti-establishment attitudes. And so because the traditional AI was the thing at the time, when they were coming into science, they saw this new and cool connectionist AI idea. And that was very exciting compared to the old, fuddy-duddy traditional established idea of AI. So all these factors basically culminated in sort of basically the putting off of traditional AI, basically as it's been tried, basically treating it as failure, and now we're going to just focus on connectionism, which the authors did not really like this. So they do say that the connectionist approach has achieved very useful and interesting findings. And they do work similarly to biological neurons. They're sort of an abstraction of how neurons fire, how they work. So we know neurons do produce cognition. So the proposal that AI research should focus on connectionism instead of classical AI needs to be taken seriously. If indeed the classical AI approach is a dead end compared to a connectionist approaches. But the authors declare that there are many misconceptions and confusions and irrelevances in the modern debate between connectionism and symbolism. And so they want to strip away these confusions with this paper. And then they say when they do this, it actually becomes clear that classic AI comes out on top when it comes to describing the nature of cognition. So both connectionist networks and symbolic systems fall under a certain category of cognitive theory called representationalist. For the most part, so in this category, this means that there are states in the mind, and then their function is to encode the states of the world. So whatever is going on in the mind somehow reflects what's going on in the world. And so, like in a visual problem, for example, you'll have certain neurons that light up if there's an edge in your visual perception of the world. And so these neurons are supposed to represent the detection of that edge in your visual field. And so a lot of the connectionist literature talks about connectionist processes as sub-symbolic, which makes it sound like it's not representational, like you don't have a symbol for representing. But the neural networks, of course, do represent states internally. Like you have to represent it even in a computer. So, and the people who talk about the sub-symbolic processes then tend to like this idea that the symbolic-like condition emerges from these sub-symbolic processes. And that's basically the position argued by Smolensky, which is what we're going to talk about next, the other side of the argument, that entities represented in the symbolic paradigm by symbols are represented in the sub-symbolic paradigm by a large number of sub-symbols. But the authors are going to actually argue against this, saying that even those sub-symbols are, they do have a semantics, like they are symbols in themselves. Smolensky would call them sub-symbols. So that's going to be basically the first major disagreement. So we can explore the world at various levels of analysis. So like we can look at physical system at the level of the quarks and atoms inside of the system, or, you can go up on a higher level or the macro scale and, various levels of abstraction. And so that's true for any physical system, and it's true for cognition. And so if you're going to talk about cognitive architecture, then you're going to have to specify what level of analysis that you're going to be talking about before you begin. And so because classicists and connectionists are both representationalists, any level where the states of the system encode properties of the world is considered as the cognitive level. So when we're talking about cognitive architecture, we're talking about the architecture of representational states and their processes that work on the representational states. So if you're going to, the authors say is if you're going to argue for the connectionist theory of cognitive architecture, then you have to argue that the processes which operate on the representational states of the mind are connectionist. Meaning that you have to argue for connectionism on the psychological level, not only the implementation level, because the implementation level doesn't matter. Because you can implement, say, a classical system using a neural network. So in conclusion, the issue for classicism versus connectionism is not about any of these things. It's not about the explicitness of rules, because not all classicists believe that or agree that explicit rules are necessary. It's not about the reality of representational states, because the two schools agree about this. And it's not about the non-representational architecture or the implementation level, because connectionist networks are universal function approximators. We know this. So at least theoretically, they can implement, a Turing machine in any classical architecture at the cognitive level. So it's not about the implementation level, it's about the representation. So normally the classicists and connectionists will assign a certain semantic content to something in their system. So for the classicist, this is your symbolic expressions. That's what contains the meaning of your system. And for the connectionists, usually it's for the nodes. So they'll say a certain node means something. And so the disagreement is about what primitive relations exist between the content. So in a connectionist idea, there's only causal relations because the nodes are only connected causally. That is, the state of the network is caused by the previous state of the network. So if there's a neuron that has a high activation, it's going to cause at the next time step the next neuron to activate. Compare this to the classicist, which does have causal relations, but also has structural relations, and that's the difference. So the semantic objects in classicism have structural constituents of other semantic objects. For example, if you have a conjunction A and B, this is a semantic expression, a complex expression, because there's multiple terms in it. So this expression is semantic, and it contains the semantic objects A and B. And then there's also causal relations between these, because, for example, if you have A and B, it's going to cause A and it's going to cause B. So then there's basically two primitive relations here compared to the one in the connectionism. And so while the difference seems small, the result is that the two theories treat cognitive phenomena very differently. And basically it comes down to their architectural differences. So in classical theories, you have a combinatorial syntax and a semantics for your mental representation. So usually they'll define a language of thought, whereas the connectionists don't have to do this. So in a classical language, it'll have atomic representations and then molecular representations. So atomic would be like an atomic term, and a molecular would be like a compound term, say in NARS. So the molecular representations can have atomic constituents, of course, but they can also have, other molecules as their constituents as well. It's basically infinitely recursive. And so the semantic content of a molecular expression is a function of its parts, including its constituent representations and its structure, this and symbol. So this A and B, it gets its meaning from A, it gets its meaning from B, and it gets its meaning from this and how it combines them. And so this is, I've seen this called the principle of compositionality. So there's also the structure sensitivity of the processes. So because your representations have a structure in the first place, now you can use that structure to perform a process, like a sensitive process. So, for example, blah, blah, blah. For example, if you have a conjunction, then you will have some sort of rule from P and Q to derive P. And then this rule works for basically any expression that involves a conjunction, regardless of how complex it is. So if you have even this thing where it's A or B or C and D or E or F, you can use the same rule on the same, because it's the same structure, to derive basically a different inference result. And so how is this related to the human brain? Is that the combinatorial structure of a classical model has a counterpart in the structural relations among the brain, meaning that the part of relation corresponds to physical relation among brain states. I'll just go. So basically what I'm saying is, if the mental model has complex representations and it has processes which depend on the representation structure, then we call this a classical model of AI. And this definition, if you note, is neutral with regards to whether or not there's a separate control process, separate executive control process. All you need is complex representations and structure dependent processes. So you don't necessarily need it as a separate control process, although many systems do. And it's also neutral with regards to whether or not there's parallel processing. So you could operate over multiple symbols in parallel, because that's often an argument by the connectionists that these systems are serial, so they are not as strong as a parallel system. But you actually can operate over symbols in parallel if you want. So from this definition, now we can define what is the connectionist model. And this is basically just a model where they do not have a combinatorial structure. And so because of that, your system cannot have operations which are structure sensitive. So for example, to make this more clear, consider a connectionist network, this picture up here. So normally what a connectionist will do is they'll label one of their nodes, or they'll label their nodes with symbols. So they'll have this node is A, this node is B, this node is A and B. And so then they'll basically claim that this network is doing something that has a combinatorial structure to it because of these node labels. So consider this network, and then also consider a classical machine that has the same expressions, but just in the symbolic expressions. So you have A, B, and A and B written on a tape. So what is the actual difference? If you're looking at these two systems, compare them. In the classical machine, your system has an object A and B, which literally contains other objects in the system. So when you look at the object A and B in memory, it's going to say A, it's also going to say B quite literally. And those objects are also contained in the system. Whereas if you look at the connectionist machine, it doesn't have this feature. Actually, there is an object which is labeled A and B, and there's also an object which is labeled A, and there's also an object labeled B. But there is no actual structural relation defined between these objects. For example, you could just add another node, and it could have another arrow coming off. You could rename the nodes to something else. You could put an OR symbol here instead, but you wouldn't change the weights on the connections, right? All you're changing is the node label, so it wouldn't change anything about the actual network itself. So the point is that the node labels are not the same as like a symbol in a symbolic system. They're effectively arbitrary. You can call them whatever you want, and they don't really mean anything. They're just like arbitrary identifiers for a node. And so it's pretty common for people to overlook or misunderstand this difference because they either don't understand the difference between arrays of symbols and classical machines and the node labels. They're confusing the question about whether nodes and connectionist networks have a constituent structure, with whether they are distributed, which of course they're distributed, doesn't mean that the nodes have a constituent structure themselves. Failing to distinguish between a representation with semantic and syntactic constituents versus a concept encoded in terms of microfeatures, and incorrectly assuming that because connectionist networks have network structure, the nodes also have, because they have a network structure, then they also are implementing a constituent structure, which doesn't necessarily follow. But obviously, you still have to do this in the connectionist systems because you have to ascribe some kind of intentional content to your neurons for them to be useful, to your machine state for it to be useful. So usually like what you'll do is you'll say these are some kind of sensory neurons, these kind of are motor neurons. And again, whether or not these labels have a combinatorial structure is kind of moot because just because the label has a combinatorial structure when you write it, the node itself, the actual data structure still does not have anything like a combinatorial structure. And so this is the real difference between classic and connectionist AI. Because the label doesn't play any role in the functioning of the network. They're not part of the causal structure of the machine in any way. The network will just continue to make the same transitions regardless of the labels. So although both connectionist labels and classicist expressions are both languages, only the classicist expression is a language which provides a medium for computation. Okay, so pretty good time, I think. Usually this lack of structure in connectionist representations is not recognized because the networks are graphs, and then we can use graphs to represent syntactic structure. So if you have like a symbolic expression, you can use a tree, like a binary tree, or a trinary, like a three-child tree, to have the two constituents and then the operation between them. So you can use a tree to represent syntactic structure. That's no problem, but that's not what connectionist networks are doing. They're doing a causal process. So right. they're basically doing a causal process. So in other words, the links in a connectionist network are not general pointers. They can't take on various functional significances. Instead, the links are restricted to one function, which is to carry causal activations. So again, many connectionists view their mental representations as distributed across neurons. And so it's assumed that because the representation is distributed across neurons, this means that it's also split into constituent parts. But that's not necessarily true, because a constituent structure can only exist when parts of that structure of the semantic structure are themselves semantic. So the constituency holds only on the same representational level, not between representational levels. So when you look at a symbolic system, the relations between symbolic entities A and B and A, this is a relationship on the same representational level. Whereas the connectionists are making a mistake because they're trying to argue for between level relations. They're talking about a distribution on the neural level, but again, we're talking about on the cognitive and conceptual level, on the representational level. So this is a mistake, again, arguing on the implementation level. And so a lot of connectionists will also hold that mental representations for concepts are distributed over the lower level units, and that these units themselves do have representational content. So they're actually going to argue that the units themselves have representational content. So this is the level we're talking about. And so then the higher level units are supposed to correspond to vectors of the lower level subconceptual units. So something like if you have like a mind thinking about something like a bachelor, it should correspond to something like adult, human, male, positive, and then not married. This should be like a network with this vector. And these are, they're not really supposed to be explicitly written out like this. They're supposed to be learned by the statistical properties of the stimuli, called like microfeatures. So they can really be at any level of granularity, even if we don't have an explicit English word for it, but it's supposed to be something that has a semantic meaning to it. But the problem is that although microfeature like positive male does indeed describe like a concept like bachelor, it's still, again, not a syntactic constituent. Like if you look at the word bachelor, they might be related semantically in meaning, but male is not contained anywhere in this word bachelor syntactically. It's just, it doesn't appear. And so both of these are atomic expressions, and which is argued that we need the complex expressions. So and that's basically what they're arguing, is that when you have you need a classical theory of representation. You need one with combinatorial syntax and semantics, because they basically argue this is what the human mind has, or what minds in general have, and what they need. And so the connectionist approaches don't do this, or if they do this, they don't really explain how to do this. And so what the authors want to clarify is that they're not saying that connectionist architectures can't implement classical theory of mental representation, because of course it's possible. You just implement a Turing machine with your neural network and then specify the Turing machine's symbolic language to be analogous to your classical language. And also the authors must believe that our own minds implement classical representation. And of course, our own minds are connectionist networks. So they shouldn't really have anything against connectionist networks in general, but rather about this interpretation that there is no classical architecture is what they would disagree with. And so they think you can't, that if you're going to have a combinatorial representation, you can't have that together with a connectionist system on the same level. That's what they're trying to say. They're saying you can have a connectionist network on the lower level, and maybe it will implement a symbolic system on the higher level, but you won't have them. You can't have them on the same level, is what they're trying to say. So, and so what follows from this is that in classical theory, some mental representations can be complex and atomic, whereas in the connections theory, all representations are atomic. And what's interesting about the classical model is that you have semantics and syntactic relations, and they're actually linked. Because when you combine like concepts with syntax into a sentence, into a complex expression, you now have an expression with linked semantics. And so the machine can operate over symbols using their syntactic relations, and these syntactic relations will also be semantic relations. So it's always going to be operating on like related thoughts. It's going to have basically a coherence of a train of thought, because it's always going to be transferring to semantically related content. And though connectionist models do not have structure sensitive operations, they do have learning and reasoning. So the way they learn connectionist models is by adjusting the weights between the nodes until the model predicts certain statistical properties from its inputs. And this is similar to the associationist principle of learning via stimulus response. Like, again, we're showing input-output pairs to our network. We're giving like a stimulus response, and then we reward, and then we kind of reward this connection between that stimulus and that given response. I'm using hidden neurons. And so while they like the learning aspect, the point of concern is that the learning processes here are frequency sensitive rather than structure sensitive. So the learning here is only a form of statistical modeling. And so to see how this is a problem, consider how if you wanted a system which could model just a simple logical conjunction. So say if you wanted it to infer A from A and B, the system won't be able to do this a priori, at least, because in order for it to be able to develop this kind of simple logic, it's going to have to see A comes from A and B many, many times and then form that association. So they don't like that the system basically is statistical learning only and doesn't have basically built-in logic. Okay, so here's where they say, this is where they argue for the need for productivity for this compositionality. So we know that the connectionists don't have it, the symbols do have it. The symbolic school does have it, but do we need symbols? And so there are three important features of human cognition, which are generally undisputed to exist, which are productivity, compositionality, and inferential coherence. And when you examine these three features, the authors argue that you're going to see that they require mental representations with a constituent structure. And then this is basically why classical AI exists. So if you disagree with any of these three features, then that's a completely separate discussion. So we'll go through the three features. The first feature is productivity of thought. So what this means is that your system's representations are unbounded. So the system can express an indefinite number of propositions. There's no restriction on it. Of course, the system is a finite system, so it's never going to express all the possible productive expressions that it could at the same time, because that would be infinite. But it does have it's never going to do that, but it does have the capacity to generate an infinite number of expressions. And then the way this is done in symbol systems is by combining symbols. So if you have A and B and C and D, you can combine them in all sorts of crazy ways. You can get A and B and A and C and A or B and C, A and B, all sorts of crazy complex expressions. Basically infinite, although I assume once you like simplify them, it's probably a finite set. Now compare this to the connectionist networks, which only have a finite number of nodes. And so they cannot express an indefinite number of expressions. So like if you have a network and it only has nodes A and B, then where is your node for A and B? Now a symbolic system will just create a conjunction putting them together. But your connection system, what's it going to do? Add another node. You can actually do this, but it's going to change the operation computed by your network. It's going to change the whole function computed by your network because the function and the memory are intrinsically combined. On the other hand, you actually could just add more memory to your symbolic space if you ran out of memory, because the operations are exactly the same regardless of the memory structure because they're separated from each other. And then, of course, nodes can only represent atomic expressions, which is just a whole other issue instead of complex expressions. And so some connectionists would try to parry this by saying human cognition is not actually productive. But again, that's going to be a separate discussion. But they kind of go along with it. They say if you, okay, fine, even if you don't view human cognition as productive, you can at least view them as systematic, which means that your ability to produce and understand certain ideas depends on your ability to produce and understand other ideas. And this is the easiest way to understand this is through natural language. So like you can, if you hear a sentence and you don't fully understand the sentence, you can at least understand parts of the sentence. And from there, you can do things like infer the meaning of the sentence, or you can at least, infer part of the meaning of the sentence. And then if you hear a sentence and you infer certain meanings and things like this, you can reuse those parts of the sentence and what they mean in other sentences and that are completely differently constructed, well, almost completely differently, but using those same semantic constituents. And so in this way, your capacity for language is systematic because you have a system for basically taking parts of a sentence, memorizing them, reusing them, combining them in various ways, according to how you understand how your language works. So you do have some sort of system for like some sort of system for language. And so because language is systematic and you look at it, what does it look like? Well, it looks a lot like a process with constituent structures because a sentence is a symbolic constituent structure that contains constituents that each have their own semantic meaning depending on where they're located in the structure. And so one might try to argue, okay, well, that's fine for language, but the nonverbal aspects of cognition are probably not systematic. And so like language is the special case, but you can see where this is an issue. So think about like an animal or something. It's implying an animal could learn a situation like A or B, where R is the relation, but it can't differentiate it from a situation B or A, because if there's no constituent structure, the order of the things doesn't matter. So it'd be pretty hard to think about a situation where an animal couldn't differentiate, say, left from right. So now we'll move on to compositionality. So the expressions you work on are you work on them systematically, but also these expressions are not arbitrarily related. Because if you understand a sentence like John loves the girl, then you can understand a sentence that's pretty much the same thing, just rearranged. The girl loves John. On the other hand, there is no relation, syntactic or semantic, between these two sentences. Quarks are made of gluons, and the cat is on the mat. Those are two completely unrelated sentences. And so you can see that somehow the systematicity of language or thought is also related to its semantics and its syntax. Now you might say, okay, this is obvious because the semantically related sentences share the same syntactic constituents, like the same words. But for this to actually be true, you have to assume the principle of compositionality. And basically, like if you're going to assume this, you have to assume that each of the words makes approximately the same semantic contribution to each expression in which it occurs. So for example, when you look at the sentence, John loves the girl, and the sentence, the girl loves John, you have to assume that each of these words provides the same semantic contribution in both expressions. So the girl rather, provides the same semantic contribution, and so does John. So does loves. And then in this way, this allows you to ensures that if you understand one sentence, then you can understand the other because you can understand their constituents. And so this explains the way that expressions and constituents are treated to produce systematically related sentences. And so by assuming compositionality in your language, you are now assuming your constituency. And as we mentioned, syntactics and semantics are related, so it's very easy to, from a given sentence, pull a semantically related sentence. And now we'll look at coherence of inference. So the syntax of a mental expression helps to determine its semantics and causal role. So a conjunction A and B will entail A, it will entail B, and psychologically, thoughts like P and Q will tend to cause thoughts related to Q and related to P. And so classical theories predict that inferences of a similar logical type will give similar cognitive capacities. So you'll never find a cognitive system that can produce P from P and Q, but it can't produce P from P and Q and R. So it's going to have basically this universal logical rule. And then you compare this to a connectionist network where there is no such systematicity in inference, because you could design a system pointing from P and Q to node P. But what if you then have a node P and Q and R and you decide not to point it to node P? Your systematicity is gone in inference. And so in summary, you can see there's a common theme in all these arguments, that if you believe that your mental account must have systematicity, it must have compositionality and semantic coherence, then you need a system which has structured mental representations. In contrast, the connectionist networks do not have structured mental representations because every item is treated as an unordered list. This means that consequently, operating purely on connectionist principles, any collection of representational states is a possible mind as long as they are causally connected. This means there's nothing preventing connectionist systems from being arbitrarily unsystematic. This is an issue because the systematicity is obvious in all cognitive systems. Without it, there is nothing to stop the cognitive system from acting nonsensically. You can be able to engineer systems which appear to behave sensibly, but you cannot guarantee it. And I thought this was a really interesting way to put it, because we kind of see this in the modern day large language models like ChatGPT. They've effectively engineered a system which, for many intents and purposes, looks like it's being systematic, but there is no guarantee. And so that's why the ChatGPT will sometimes just plop out things that don't make any logical sense, because it's a form of it's just operating purely on connectionist principles without any classical principles. So what is the lure of connectionism? Firstly, brains and computers operate differently. Obviously, brains are parallel networks of neurons, and a conventional computer program follows sequential instructions. And so brains can compute many, many operations all at the same time very quickly, whereas a conventional computer has to take a lot longer to perform the same computation because it has to do it serially. Also, the traditional classic AI had difficulty with pattern recognition in the conventional architectures. So human brains are almost effortlessly able to memorize patterns and very even nuanced patterns, distinguishing them from tens of thousands of other even very close patterns. And so if you wanted to search through your memory serially to compare all these patterns, it would be so complicated, it would overwhelm any computer. And so your pattern retrieval has to be stored in a different and retrieved differently in a different way than as in a conventional computer. Classical AI models have different rules, manual rules for rule-based versus exceptional behavior. So usually they have a mechanism or a rule set for regular or uniform behaviors, and then they'll have a separate mechanism which allows some slight divergence from this rule set. And so it's kind of complicated, because when do you allow the regular rules? When do you allow the divergent rules? And so this is kind of hard question. It'd be a lot simpler if you could use a connectionist system, which is a lot more elegant because you only have one single rule set, the causal rule, which governs the whole system. Then you only have to worry about that one rule. Lack of progress in dealing with nonverbal and intuitive processes. This is basically the same as the pattern recognition issue. It seems really hard to describe sensory signals or motor programs with language or with symbols. Instead, humans have like sort of an intuitive or subconscious knowledge about, say, how to walk. So it'd be really hard to get a symbol-based computer system to, like, for example, figure out how to have a motor program how to walk. And so it's argued that motor programs must be stored in a non-linguistic or more implicit form, as in neural network weights. Sensitivity of conventional architectures to damage and noise. Brains are very tolerable to noise. For example, we have neurons that die and are born quite often. And there's also like electric noise and the electrical activity of our brain. So like things vary slightly all the time. And even so, it doesn't really majorly impact the behavior of our brain. Our brain can also tolerate physical damage. So like if you got in a car accident or something, literally part of your brain just like chopped off, you would have some issues, but actually for the most part, you'd still be able to perform a wide variety of functions and like live to it, to a certain degree, depending on how much of the brain is. Now compare this to this is suggesting obviously that the mental representation and your cognitive skills aren't located in any one specific area of the brain. They're more spatially distributed. So when you lose part of your brain, you might lose part of a functionality, but not even the whole functionality necessarily. Compare this to a conventional computer, where it will catastrophically fail if any noise or damage is introduced to its values. Like if you take some sort of computer operation, you flip a single bit in the instruction, it's going to turn into a completely different computer instruction. You might have changed it from an if statement to like a jump instruction or something. So this will just catastrophically destroy yourself. Storage in conventional architectures is passive. So the information just kind of sits there until your processor comes along and selects it to work on it. Whereas you contrast this with the connectionist system, where the information is constantly, all the information in the brain is constantly moving, constantly traversing along edges and nodes and being processed. Conventional rule-based systems depict cognition as all or none, but cognitive skills appear continuous. So for example, there's a variation in degree of applicability for different cognitive rules. So in some cases, you might want to use some rules, other cases, you might want to use others, and the distinction is more of a matter of degree than absolute decision. And for example, when humans are unable to complete a certain task, they'll at least try something else. They'll try something reasonable. And if you compare this to the conventional computer program, which is not programmed to, do something explicitly, it's going to either do nothing or it'll just fail when it encounters a task that it was not programmed to complete. It was not trained to complete. And then furthermore, the conventional AI models are dictated by the technical features of like Turing machines of computers, and they ignore basically all the discoveries of neuroscience. So classical AI systems, they don't think about neurons, they completely forego the brain, which is obviously our only known example of cognition. So classical AI systems are not implemented in neural architectures, and it's not really clear or explained by classical AI people how their framework is neurally plausible. And meanwhile, we do know that brains produce cognition, and so it seems reasonable we should take some inspiration from the neuroscience when developing an AI system, or else we risk being entirely misled by the classic AI path if it turns out it has no neural plausibility at all. So basically, we take a risk if we take the classic AI path that what if classic AI actually is not related to cognition at all, and we can't find a neural link. And so they're going to argue, they're going to defend against all these points by saying all of these arguments suffer from one of two defects. So they either say that these objections are not intrinsic to classical models. So like a lot of the objections, well, we'll get more into depth. And even though many of the classical models, this is kind of the same point, even though many of the classical models do indeed work in the criticized way, they don't necessarily have to. And these criticisms are directed at the implementation level of the classical system rather than the cognitive theoretical level. For example, a classical model could be neurally implemented. So for the parallel computation speed, connectionists say cognitive processes need large-scale parallel computation. Their response is, this is actually irrelevant because we're talking about the cognitive level, not the implementation level. So it's just irrelevant, they say. Resistance to noise. Again, this is aimed at the implementation level. There's no reason to believe a classical architecture implemented in a distributed manner could not also be resistant to noise. Soft constraints, continuous magnitudes, active symbols, etc. Again, this criticism is aimed at the current implementations, not at the cognitive level. So one could implement a classical system that decides to execute certain rules based on continuous values, or a system that executes various rules all at the same time, deriving various conclusions. Explicitness of rules. Again, this is aimed at the implementation level. Classical AI scientists disagree about how much the rules need to be explicit versus implicit. There's only agreement that there has to be some non-zero amount of implicit rule-like behavior, and that the machine does explicitly store symbols in its memory. though the symbols are not related to the rules, but only the memory representation. And for brain style modeling, for people who claim that we need to model model AI systems like the brain, they counter with how close does it have to be modeled? Because the connectionists themselves do not model biological neurons very accurately. Some people use very, very idealized abstract models of neurons. Like Smolenski is going to argue, for example, that his is not on the neural level at all. And some people do try very, very hard to make biologically realistic simulations of neurons, as in the Human Brain Project. But again, most people are somewhere in between, where they don't really think about it too much. And it is without question that we would be better off to know the details of the cognitive level and the neural implementation level. Of course, this is basically the primary question in cognitive science: how do these things link? But the question is, like, what do we gain from just modeling all sorts of random neural networks without really trying to explain how they even work on a cognitive level? And so we can answer that in the present day, because it seems that in AI, neural networks are very popular because they simply work. And these previous AI systems simply didn't work. And so that satisfies most people. But the problem is that they're forgetting that even though these systems do work, you might be neglecting something about the theory, the cognitive theory. So in conclusion, the implementation of cognitive architecture is irrelevant to the cognitive theory. In the study of cognition, we are talking about the abstract theory, not the implementation. Obviously, we are interested in the implementation when we're making the computer program, but in our theoretical discussions, it's not as important. Most arguments that are pro-connectionist or anti-classical are invalid because they are levied at the implementation level, not the cognitive level. And it actually does make really good sense to use connected neural networks to model cognitive theories, classical cognitive theories, if it turns out to be helpful for us. The problem is that in the modern day, no attempt is being made to link neural networks to classical cognitive theories. And so many hard to explain troubles are arising in the connectionist architectures, for example, unreasonable behavior and catastrophic failures.